Okay, looking at this assignment from last time, do we have any questions that we want to deal with? Questions? Harley? Number 4. Okay. So it says you deposit $5,000 on January 1st, 1998 into a bank account that pays 5.5% interest compounded weekly. Write an exponential model where FV represents the value of the account after T years. So if I just fill in my values, remember there's 52 weeks in the year, so if we're compounding weekly, N is 52. So there's my model. Okay with that? Okay. It asks, what is the account's value January 1st, 2012? So if I compare January 1st, 1998 to January 1st, 2012, that has been 4 years. So T is equal to 4. Oh, 14. Thank you. Yes, 14. So I go ahead and I do that. So I get 10,794.44. Okay there. And then part C says, after how many years is the account worth 15,000? So to do this, we're going to have to solve by graphing. So my first equation is just going to be my model. Okay. And my second equation is going to be 15,000. And then I'm going to have to set my window. So again, X is years. It took 14 years to get to 10,000 and change. So I don't know, by 30 years, we should definitely get to 15,000, right? So maybe I'll go 0 to 30. That seems pretty reasonable. Yes. Yep. Yep. I just used the variable x. So x is t and y is fv. Since they're just names, you can name them anything you want. So the calculator says y and x, so I just use y and x. Okay with that? And then my minimum y is the 5,000 that we start with. And I need to get to 15,000, so I'm just going to pick something bigger than 15,000, maybe 20,000, just for round number sake. And let's hit graph. So again, when choosing these windows, there's no such thing as a right window or wrong window. As long as you can see the intersection, you have a window that's good enough. So you notice here on the page, we can see the intersection right there. To find that, we can press second trace, select the intersect command, first curve, second curve, and then scroll over for the guess. And we get about 19.99 years. So I should probably say, be specific there, 19.9 years after January 1st. Or approximately, what, in 2018, right? It's basically 20 years. Everybody okay there? So all the problems are basically the same as that. They all kind of follow that same pattern, right? Write the model. Part B is plug some number into the model. Part C is plug some number into the output and solve for the exponent. It's kind of all the same. Caden? Uh-huh. Okay. So it's asking for an account value. So that's FV. That's what we're looking for. And you're given a time. So I just have to turn that into some kind of value for T. So because 2012 is 14 years after 1999 or 1998, we used 14 for T. Okay. I think we did an example similar to that in the notes even that day, right? Where we've given dates and had to convert that into a T. I think one of the examples last time we did that even. Other questions on these kinds of problems? Okay. Next topic then is we're going to talk about the natural base. Yes. And the symbol we use to represent that number is the letter E. So let's go back and think about this model here. So in this model, what we're going to be interested in talking about is this value for n. So n represents, remember, the number of compounds per year, right? That's basically the number of times your account value changes in a year. What we're going to do here is we're going to extend this idea to think about systems other than just like bank accounts and banking. And we're going to extend this to think about some like biological systems. Okay? So let's imagine that we're describing like the weight of a baby changing over time. Okay? So how often is a baby's weight changing? Often, every day. I'd say even more often than that. More often. More often. Yeah, like it's changing all the time. There's an infinite number of compounds or an infinite number of changes per year, right? If something's growing, it's just like always growing, right? You could also extend this idea if you have a very large population. So let's talk about human beings on the planet Earth. About how many human beings do we have on the planet Earth? Yeah, 7 billion or so. How often is that population changing? Like all the time, right? People are dying or being born. It's happening all the time. The population is changing, right? Basically, it's infinite number of times that population is going to change every year. So this is a very natural thing to think about when you start talking about these biological systems, being interested in things that are changing continuously. No, things could be decreasing. Sure. Think about like it was, like 80 degrees yesterday at noon. Right, so that's fine. Things can go down. So if it was like 80 degrees yesterday, and then the next, later on that night it's 65 degrees, you covered all the temperatures between 65 or 85 and 65. Like infinitely many of them because you have as many decimal points as you want, right? Temperature is kind of continuous. So you could have something like that where things are decreasing and not necessarily increasing. Does that make sense? Okay. So what we're going to be looking at here is this value for n when it gets really, really big. So to study that, what we're going to do is we're just going to kind of set all the other parameters to 1. So this is just going to turn into FV equals 1 plus 1 over n to the n. And what we're interested in is what happens when n gets really big, when it starts going towards positive infinity. Now, can we just plug infinity symbol in for n and evaluate this and get a number? No. But what we can do is we can plug progressively larger values of n in and look at kind of see if there's a pattern happening. So that's what we're going to do. So I'm going to make a little n FV table. So I'm just going to pick n's that are getting larger by 1 order of magnitude each time. And we'll just pick a couple. And by that point, we'll get a decent idea of what's going on, or we should. Okay? So when I plug 1 in for n, I just get 2. When I plug 10 in for n, I get all of that stuff, 2.593744246. When I plug 100 in, I get 2.704813829. When I plug 1,000 in, I get 2.716923932. When we plug 10,000 in, we get 2.718145927. Let's take a little bit of a pause here. So, in general, what would you say that's happening to FV as n gets larger? It gets larger too, right? Now, and in the beginning, is it getting larger by the is FV getting larger by the same amount each time? No. Is the amount that FV is increasing, is that getting bigger or smaller? The amount that FV is increasing is getting smaller at each step, right? Eventually, what do you think that amount is going to be when n gets to infinity? 0, right? So what we're going to say here is that FV is eventually going to stop changing as n gets large enough, right? So if we notice here, as we go step by step, after the first step, the first digit is constant, right? And again, still stays constant. At the third step, we notice that the first 2 digits are now the same, right? And at the next step, the next 3 digits are all the same. If we continue going, we'd expect as n gets large enough, we'd be able to like lock in the however many digits we want. We just have to keep picking larger and larger and larger values of n. We don't really know what that number is for FV when it stops changing. We don't know what that is quite yet, but we know we can get as many decimals of that number as we want just by picking a progressively larger and larger and larger value of n. Do you guys kind of see that? Okay. So let's plug the 10,000 in and we'll stop there because quite frankly, like you guys get the idea, right? All right. The last number there for our table is this. So what we're going to say is that as n approaches infinity, 1 plus 1 over n to the n is equal to e. So the symbol that we're going to give to this number that we've been kind of chasing is going to be the letter e. This letter is like, this is an irrational number, just like pi. It's a decimal that goes on for forever, but it doesn't repeat. It's another irrational number, just like pi. So we're going to give it a symbol, just like we give a symbol to represent the number for pi. And this number is programmed into our calculator, just like the number for pi. So if I press second and the division symbol, that gives me this number e. If I press enter, here's the first, I don't know, whatever, 10 digits of e. So it's about 2.718281828. Continues going forever. It doesn't repeat. There's no repeating pattern to this number. It's irrational, even though it looks like there's some repeating 8s and 1s and 2s in there. There's no pattern to it, though. It just keeps on going forever. Go ahead. Okay. There's a second way to access this e on our calculator. So if you press second and the button that says ln here on the left side of our calculator, it also gives us the letter or the number e, but it automatically gives us an exponent with it. This is probably the version that I would use more often than not, because in this chapter we're going to be putting an exponent because we're using e as like this part of our exponential function. So that's how we can get e on our calculator. So what this does now is it allows us another model. So now we can write the exponential model for continuous change. So that model is FV is equal to PV times e to the RT, where FV is just some future value. PV is just our present value. E is that number 2.71828 yada yada yada. R is our rate of change as a decimal. And then T is our time. And the unit for time should match whatever the rate of change is. If the rate of change is yearly, time should be in years. If the rate of change is hourly, it should be in hours, etc., etc. So let's do a couple of little examples now. So there's two kinds of problems that you can run into where we have this kind of continuous growth or decay going on. One of those problems is we give you the model to use and you just have to do some problems with it. So for example, the length L in centimeters of a tiger shark can be modeled by L is equal to 337 minus 276 e to the negative 0.178 t, where t is the shark's age in years. Yes, of course. So here we've just given you the model to use in the problem, so you didn't have to write your own. And the first question we're going to ask is to estimate the length of a 3-year-old shark. So what parameter am I looking for my model, L or T?
L.
L, because we're asking for a length. So to find L, we need to plug in a value for T. What value of T are we going to plug in? 3, because that's how old the shark in question is. And T represented the age of the shark in years. So I'll just type this into my calculator exactly as it looks. So 337 minus 276, and then second, and ln calls the e with an exponent on it. And then in the exponent, I'm going to type negative 0.7178 times 3. So I get about 175.2 centimeters. Yeah. Okay. The other thing that we can do with this is we can ask questions like, estimate the age of a 3-meter shark. So which parameter are we solving for in our model here? T, because we want the age of the shark, that's a time. So to solve for T, we need to have a value for L. L is length in centimeters. So what value of L should we plug in here? No to 175.2. No to 3.
No, like 300.
300, yes.
I was saying 337.
Yeah, and now I started writing 337. Yeah. Okay. So we'll solve this equation now using our calculator just like we did before. So I'm going to do 337 minus 276 second ln negative 0.178x and then 300. Okay. And then we'll go to our window. Who knows something about sharks, at least a little passing knowledge? How old can a shark get? Pretty old.
100, yeah.
Okay, like 100 years? Sure, why not? Okay. And then my y min, so the y's are the length of the shark. What's the shortest a shark could be? 0, that's one that hasn't been born yet. And my maximum length of the shark needs to be at least how much? At least 300, right? So I'm going to pick 400 just for a round number. Sound okay there? So let's hit graph and then we can find the intersection. So this is my curve for the length of the shark. There's my line for 400. So I can see the intersection happens right there. So if I go second trace, select the intersect command, first curve, second curve, just a couple of enters there, and then scroll over for my guess. I get 11.3. So that shark would be about 11.3 years old. What do you guys think there on this one? No big deal, right? So they gave you the model already. That usually makes life a little bit easier because you don't have to write anything yourself. Let's look at another question where we don't give you the model and you have to write your own. Okay, so you deposit $2,500 into an account that pays 5% interest compounded continuously. Find the account value after 10 years. What word in that story prompt should jump out to you in bright red flashing letters as the most important word in that paragraph? Continuously. Why is that so important? It tells us the model that we need to use is this model rather than the compound interest model. So we got to be careful when we're reading and look for that word continuously because it's going to tell us which kind of model to use. Everybody's okay with why we're not using the regular compound interest model? Okay. So we'll just fill things in as we would normally. The present value is the 2,500. E is just the number E. R is 0.05 and T is 10. So now I can just type this into on my calculator. And we get $4,021.80. Is everybody okay there? So not much changed, right? The only thing that really changed in doing those problems was what model to use. But it's easy to see which one I would want because all I'm doing is looking for the word continuously. Yeah. Okay? Good. Next up, remember when we talked about the start of this chapter, we said we're going to talk about exponential and logarithmic functions. We have yet to mention this word logarithm yet, or logarithmic functions. It's time we start talking about that. So we're going to start talking about logarithms today, just a little bit. But before we talk about logarithms, I want to do a little bit of a recall here. So I'm going to ask you guys to do something very hard, which is to remember back to the beginning of first semester. So, who remembers what the definition of a function is? Who remembers what the definition of a function is? Harley. Okay. So that's fine. Let's call it a set of ordered pairs. That's going to be our list where every x pairs with exactly one y, which is basically none of the x's are being used more than once, right? So we need some kind of a pairing going on for our function. Okay? So in like the most abstract sense, we defined a function, or we said something like this represented a function, right? Because none of the x coordinates repeated each. Yes? You guys kind of remember this? Okay. What I want to talk about now is an inverse function. This is something else we talked about there. Does anybody remember what an inverse function is? Okay. So just in an English language sense, what does the word inverse mean? Reverse or opposite or something like that, right? So what do you think the inverse for this function that we just wrote down would be? 2, 1, 3, 2, and 4, 3. So when we talk about an inverse function, we're talking about swapping the x's and y's, right? Everybody kind of remember that? And now this is easy to do if our function is described as a list of ordered pairs, but we know functions don't have to be described that way, right? We could also describe a function as an equation, maybe something like 2x plus 5. Do you remember how to find the inverse when a function is written this way? Okay, well, let's define what we mean by an inverse then first. So we say that the two functions f and g are inverses if and only if f compose g of x equals g compose f of x, which is equal to x. So let's say, for example, we have f of x equals 2x plus 5, and g of x is equal to x minus 5 over 2. To check that these are inverses, I need to do f compose g. Does anybody remember how we do that? Is we're going to take the expression for g and plug it in for the x's in the expression for f. Everybody okay there? Notice that I have a multiply by 2 and a divide by 2. Do you guys see that? So those will cancel. And then I have a minus 5 and a plus 5. Those can cancel. And I'm left with x, which is exactly what I'm supposed to get if these two functions are inverses, right? Okay, so we've seen kind of what the definition of an inverse looks like if we're talking about a function represented as an equation, which is really how we've been representing our functions ever since the first chapter, right? We gave up on this set of ordered pairs thing pretty quick. So there must be an easy way to figure out what that inverse function looks like, because Mr. Kulik did it really quick in his head to generate that example. So let's go back to this function here. The way that we find its inverse is I like to start by rewriting the f of x just as a y. Remember, those really mean the same thing, y equals and f of x equals. And then I'm going to get the x by itself. So I'll subtract 5 from both sides. And I can't combine a negative 5 and a variable, so I'm just going to write the minus 5 right next to the variable. And then I'll divide both sides by 2. And again, I can't divide a variable by 2, so I'll just write the 2 as a fraction. And now the x is all by itself. Everybody see that? My last step then is to swap the x and y variables. So everywhere there was an x, I'm going to write a y, and everywhere where there's a y, I'm going to write an x. And so I'll just give this function now a new name. So there is my function g of x that will be an inverse to f of x. Harley? Sure. Do you guys kind of remember doing that from way back in first semester? Because we did it. I promise we did. Now, the reason that I've gone ahead and did all this review here is because exponential functions and logarithmic functions are inverses of each other. So it's really kind of critical that we remember those kind of definition of what it means to be an inverse. So back to logarithms now. So we say let b and y be positive numbers with b not equal to 1. The logarithm of y with base b, which we denote as log base b of y, So the way we read this string of symbols is we say log base b of y. So that b is a subscript. And we say that the logarithmic equation, log base b of y is equal to x, is equivalent to the exponential equation, b to the x is equal to y. So let's say we have log base 2 of 8 is equal to 3, and we're asked to rewrite this in the exponential form. So to do this, I'm going to use my definition of a logarithm. So I notice that the b in my logarithmic equation is 2. So that's going to give me the base for my exponential. The y in my logarithmic equation is 18. So that's going to give me the solution to my exponential equation. And the x in my logarithmic equation is 3. So that's going to give me the exponent in my exponential equation. And if we look, is 2 to the third equal to 8? Does that make sense? Yeah, that's true. Let's do another. Okay. So let's say we have log base 6 of 36 is equal to 2. What is the base of my exponential equation going to be here? So the b in my exponential equation is going to be what number? 6, because it's the base in my logarithmic equation. Okay. What is the exponent in my exponential equation going to be? 2, because that's the solution in my logarithmic equation. And what is the solution to my exponential equation going to be? 36, because that's the argument in my logarithmic equation. Olivia? Of course. So what is this logarithm really giving me? It's giving me the exponent in an exponential equation. Remember all of these problems that we had to solve by graphing in the previous sections? What we're going to be able to do here in a day or so is be able to solve these now algebraically by using a logarithm. So that what the logarithm is giving us to is giving me the answer to something like 2 to what power gives me 7. What the logarithm is telling you is the exponent that needs to be on 2 to give you 7. Now that's not a whole number, right? We know 2 to the second is 4 and 2 to the third is 8. So it's going to be some crazy decimal in there. Okay. So let's do the reverse idea here. So let's say we're going to rewrite the exponential equation, 5 to the third is equal to 125, as a logarithmic equation. So we say log base 5 of 125 is equal to 3. So there's my base, the solution is my argument, and the exponent is the solution. Is everybody okay moving back and forth between these two? Should be pretty easy, right? You're just looking at the two forms and putting the numbers in the right places, basically. So what if we ask now to evaluate, say, log base 7 of 49? So the way I'd like to think about this is as a logarithmic equation. So I'm saying log base 7 of 49 is giving me x. If I rewrite this as an exponential equation, I'm saying what power of 7 is equal to 49? And we can solve that by inspection, right? That's easy to see. The answer is going to be 2. Everybody okay with that idea? Okay. Let's stop here.